All right, we'll go ahead and get going here. So we got this graph going on. The blue line is the representation of all the ordered pairs that exist for this particular function. This would be a function that does pass the vertical line test out of that, and it's got quite a few things going on. It's got several places where it's crossing the x-axis, only maybe one place where it's crossing the y-axis. We see a lot going on with this graph. We see no repeated x values, but a lot of repeated y values throughout here. So that's going to come into play. The first thing we want to answer is this first question that I've got written over here. What is f of 0? So what does that mean it's asking for? F of 0 represents what? Where y is 0, where x is 0, it's the y value for when x is 0. And so what is the y value for when x is 0? 4 is right up here. That place right there. That's the only place where x is 0, if the y value is 4. The answer to that one would be 4. All right. Now, get into this fun stuff, the domain and the range of this particular graph. We don't have an equation for this, so we can't do something equal to 0 or greater than or equal to 0 to figure that out. But we can see the graph, so we could get the domain from there. The domain is related to which values, x or y? X's. So domain is going to traveling left to right. So what's the lowest x value? 0. What's the highest x value? 4 pi is the highest one. So the domain would be from 0 to 4 pi. And I'm putting brackets on both of those because they're both filled in dots. If one of them was an empty circle, like a hole, then you would use a parenthesis for it, but they're both filled in, so there are brackets on that. So that interval notation is really easy for that when you see the graph. It's actually easier than set notation for that. The range, since domain dealt with x values, range obviously deals with y values. What's the lowest y value? -4. The highest y value? +4. Okay? It's repeated several times, but that really doesn't matter. It's still a range from -4 to +4. Okay? And we got that going on. So we found a value for y when we get an x value. We got the domain, we got the range. Let's talk about same graph. Try to scroll where you can still see it. The intercepts, and we'll start with x-intercepts. Okay, x-intercepts are where the graph crosses what? The x-axis. How many are there? 4 for this one. List them. Okay, the ordered pairs. So we would have pi over 2, 0. 3 pi over 2, 0. 5 pi over 2, 0. Or 7 pi over 2, 0. We have 4 x-intercepts. What about y-intercepts? One of them. Where is it? At 0, 4. We've got our y-intercepts. We have intercepts for the graph. When they ask for intercepts, they're asking for x and y-intercepts. A lot of times in math, we focus on the x-intercepts when we're talking about polynomials. When we're talking about lines, we usually focus on the y-intercepts. But they're asking for both in most cases here. Interesting question here. Where, excuse me, is f of x greater than 0? So if we're looking for that in the graph here, where is that thing greater than 0? Remember, what does f of x represent? F of x is what value? Y values. So where are the y values greater than 0? The y values there were highlighted. Are they positive? Yeah. So there's a place. The interval notation for that place would be what? From 0 up to pi over 2. Do we include pi over 2? No, because it's not positive there. It's equal to 0. So we have from 0 to pi over 2. Then we have from 3 pi over 2. So I'm right here. It's positive all the way around this loop here till we get there. 5 pi over 2. So from 3 pi over 2 to 5 pi over 2. That should be a bracket on the 0 because it is positive. Brackets or parentheses on each of those? Parentheses, definitely parentheses, because their y value is 0. And then one last place, looking at our graph, starting here at that spot and going up. So from 7 pi over 2 up to 4 pi. 7 pi over 2 to 4 pi. Notice that what values are we reporting here? What are these are x values, not y values. We're looking for y values that are positive, but we're reporting x values. X values is our location where we're at on the graph. Y values is the value of the graph, basically. It's the way I've always kind of held that, is that you need to report x values, look for y values, but report x values on that, okay? Where does f of x equal -4? Where at? Pi and 3 pi. X equals pi. X equals 3 pi. Good places for that. And I get question 7. Question 7. How many times would y equals -2 intercept the graph? Y equals -2. What does the line y equals -2 look like? Yeah, horizontal line going straight across at -2. So if I went up here to the graph, I could draw that, this little dotted line here. That's y equals -2. How many times would it intercept that? 4 times. Okay. Now, we would have to have a little bit more information about the equation of that function in order to find those actual values. We could estimate what they were by looking at the ordered pairs, but we're just looking for how many times they're, not anything else. Okay? All right, example B. I've already got a red flag thrown on there. Hopefully that's not a surprise that he had a red flag on there. Because if we're looking for the domain of f of x being x plus 1 and x plus 2, over x plus 2, excuse me, the red flag is where? And why? Well, I guess is a better question. Why the red flag? X in the denominator, right? So the domain comes from setting the denominator equal to 0. We know x cannot be -2. So I set up that in set notation. in interval notation, what would that be? Excuse me. What's the interval notation for that? Negative infinity up to -2, parentheses, not square bracket because the -2 can't be used. We're skipping -2. Everything else is okay, but the -2 has to be hopped over. Question 2 for this particular function. We don't have a graph for this one. We just got the equation. But they ask us something about the graph. They say, is 1/1/2 on the graph of this function? How could we tell without having the graph? That's a great idea. If I did f of 1, if it's on the graph, what should it end up being? It should end up being 1/2 if it's on there. But in this case, it ends up being 2/3. So is 1/1/2 on the graph? No. 1 2/3 is on the graph, but 1/1/2 is not on the graph. There, so we can't say there. Where does f of x equal 2? Maybe that's a little more interesting problem. I don't have the graph for that, so I can't just draw me a line y equals 2 on it. And maybe that wouldn't be the best way of getting there anyway. How could I do it algebraically? I've got this function f of x is equal to x plus 1 over x plus 2. I want to know, where does f of x equal to?
X plus 1 over x plus 2.
Yeah. Perfect. Setting it equal to 2. Technically 2 over 1, same thing. And then how can I solve that? Taught this today in Algebra 1 at school. That would be a proportion, wouldn't it? Because it's a fraction equal to a fraction. And the way you solve proportions is you cross multiply. Remember doing that? That'd be 2x plus 4 equals x plus 1. And solve that for x. Subtract. Brain's doing it before my hand is. Subtract x from both sides and subtract 4 from both sides, and we get x equals -3. Where does f of x equal 2? At x equals -3. That's where it exists at. Okay. So setting the whole problem equal to 2 to find out where that's happening. Now, the next piece that we want to take for this particular function, again, we're dealing with f of x is x plus 1 over x plus 2, just so I don't have to scroll back and forth. That's our function, and we want to find the intercepts. And remember, with intercepts, we're not only finding x-intercepts, we're finding y-intercepts as well. Okay? So, how do we find y-intercepts? That's x-intercepts. When x equals 0 is a y-intercept, right? So f of 0 so the y-intercept's at 0, 1/2, or 0.5, whichever one you want to call it. I prefer the fraction method, but some of you may be like decimals. I don't know. X-intercepts is where y equals 0. A little bit more work involved there, but not much. Because technically, it's just like we did when we're finding where f of x is equal to 2, except for we got easier math to do. Because if I multiply both sides by x plus 2, x plus 1 equals 0. So that thing crosses the x-axis at -1, 0. And that's the only one. It's the only place it crosses. And find the intercepts based on that. So being able to take a graph and find those things from it, like that first example we did, or take an equation and find various things from that based on just basic knowledge about intercepts and domain and range. Still, if it's an equation, you're still looking for those red flags like we were in section 1. If it's a graph, you're looking actually at x's, left to right, y's up and down. So it's really just look at the picture and figure it out, that sort of thing. So that's section 3.2, and I'll go ahead and write on page 224 in the textbook that we have 9 through 47 odd is what you could look at for that if you want to do some practice problems before the Canvas quiz. Okay, I'm just going to go ahead and jump into 3.3, and it's properties of functions. A little bit longer lesson here on this one than it was 3.2, so not incredibly difficult here, but definitely a little longer stuff. So buckle up. Properties of functions. Functions can be odd or even, and there's an odd or even function test. If f of negative x is equal to f of x, then f of x is even. If f of x, or f of negative x, is equal to negative f of x, then f of x is odd. Any other configuration of f of x happens if you plug in a negative x and work it out, simplify it. If anything else happens where some of the signs change and some of them don't, then it's neither. So functions can be even, odd, or neither. And if they're not even and they're not odd, they're neither. Just like the number 0. 0 is not even, 0 is not odd. It's neither. Okay, so that sort of thing. Functions can be that way. The graphic rules for that. So that's the algebraic test, and we're going to do that most of the time. But the graphic rules. So by graphic rules, I mean what the graph looks like. Graphic rules for odd or even functions. An even function is symmetric with respect to the y-axis. Okay? Symmetric, what does symmetric mean? Same on both sides. It means if you folded it across the y-axis, hot dog style like that, that it would match up on each side. They're exactly the same on both sides, symmetric. So even functions, symmetric on the y-axis. Odd functions, a little bit more difficult to see on a graph. An odd function is symmetric with respect to the origin. Okay, that one's a little bit tougher to see because it basically takes folding across the y-axis and then folding across the x-axis. So you got to visualize a little bit more that you would fold it across the y-axis and then fold it down, and it should match up if it's odd. That's a little bit more difficult to visualize without actually folding it. But the algebraic test is a little stronger if you've got the function equation to deal with there. So we'll look at both of those as we go along here. So example A for this section, we're going to answer this question. Is the function even, odd, or I say neither. You may say neither. I don't know which one is correct. You hear them both. So we're in Tennessee, so it's neither. Well, so even, odd, or neither. All right. So we'll start with one that we've got the equation for because I like the algebraic. I like algebra a whole lot, or I probably wouldn't be doing this for a living. So here's our function. F of x is equal to 6x squared minus 3x to the fourth. Doesn't really matter that that's a high degree polynomial, and we haven't done anything with high degree polynomials yet. But it's all based on even odd rules. Technically, the rule is plug in negative x and work it out. I hope that everyone can see that there is a shortcut to that. Because what happens when you have an even exponent on a negative? It turns it back to positive, right? So that's going to make it 6x squared minus 3x to the fourth. And that is the same as the original. So that would mean this one is even. What do we notice about the exponents on every variable here? They're all even, right? That goes together, not a coincidence. Okay? Things are not a coincidence in math class. H of x. X to the second plus 7x plus 12. Technically, if we plug in negative x, here we get x squared back. That changes the sign of the 7x to negative, but the 12 stays the same. Did everything change? No. This would be a neither. If you had something like simple c, g of x, negative 8x cubed minus 5x, technically, the rule is plug in negative x. Negative to an odd exponent turns out to be what? Negative. Negative x cubed times negative 8 makes it positive x cubed. Negative 5 times negative x makes it positive 5x. Did that change everything? Yes. So it's odd. What are the exponents on the variables here? 3 and technically this one is a 1, right? They're both odd. So if all the exponents on the variables and everybody has a variable and all their exponents are odd, then it's an odd function. That's what's going to happen. Then it's going to be a neither. Yeah, that's exactly right. Still going to be a neither. They've all got to match and be even for it to be an even function. They're all got to match and be odd for it to be odd. And any other combination is a neither. Most functions that you're going to encounter in life are going to be neither. Odd and evens are kind of special. And we see that with the graphic rules that to be symmetric by the y-axis, that's kind of special, right? To fold and match up. To be symmetric by the origin is even more special because you got to fold this way and then you got to fold down and match up. So that's really special to be able to do that. So most functions that you see are neither, but in this section, they're trying to focus on the odd and even stuff. If you got a graph, so I'm just going to sketch some graphs here and try to be what I'm trying to represent. I'm meaning for that to be what? Even. Because I can fold it across the y-axis and it's symmetric, is what I'm trying to shoot for there. Symmetric, odd would be symmetric about the origin, so I would have to be able to fold it and then fold it down. And if I folded that down, I definitely don't have a loop in the bottom like I do in the top, so we know it's not odd out of that. The odd ones are tough to draw, so I'm going to do my best here. Try to draw you one. So here's a... I did pretty good. Yeah, definitely odd. Fold it across and then down. You can see it's going to match up there. Most of the time, odd functions go through the origin, actually. I mean, that's not always the case, but it does happen quite often. How about that? The neithers are easy to draw because you just make something else up that doesn't work. Something like this. That definitely does not work. I fold that across and fold it down. I end up with a lot of mess there. So that would be a neither on the graph. So fairly easy stuff there. All right. So the next thing, and I'm going to cheat a little bit here and go get a graph that I've already drawn and copy it. All right. I've got example G here. That's what this should be. Got this graph and some stuff going on there. So you don't have to be just incredibly precise on this. I'm going to try to be, as lenient as I can on it, and just get close. Like that definitely is not right there. Let's make that 6-1, and it works. There we go. That's a little better. And then my grid is definitely not to scale, but that's okay. Should have done this on graph paper, but I didn't. All right, so we got these ordered pairs. That's the big thing. All right, what we want to talk about here is intervals of increasing, intervals of decrease, and constant intervals. So if it's something that's increasing, we read a graph from left to right. So increasing would be increasing from left to right. Decreasing would be decreasing from left to right. So getting lower from left to right. Constant, staying the same from left to right. Okay, so there are various intervals in this particular picture that do those things. And so the first thing that I want to do with this problem is just state the domain. So this is similar to what we did in 3.2 with that picture of the trig graph that we had. What's the domain of this graph? What's the smallest x value? -6. The biggest x value, +6. Those are definitely included. So brackets on those. So there's our domain of this graph. We can go ahead and state the range. Range is always something that's good to know. What's the lowest y value? -2, and then that shouldn't be there. That's giving you an answer. The highest y value, 4. So there's our range. Okay. Now, let's get some intervals of increase first. So increasing means it's going up from left to right. And you've got to see change in direction for it to stop doing that. So if I start on the left side of the graph, I start over here at -6 and I'm going here. What's going on as I follow the blue line here? It's decreasing from -6 to where? -4. So I see an interval decrease. So we're going to go ahead and do that since we know that it's happening. So from -6 to -4, we got some decrease happening. And I use parentheses when I'm doing intervals of increase and decrease and constants. I want parentheses because when you get to -4, -2, that ordered pair, is it stopping increasing and started decreasing there, or what? You can't tell. That's the point of inflection. Okay, so at -4, it changes directions and starts going up, and it keeps going up. We get to this place. That's an interesting place. It's actually an x-intercept. Really doesn't, but it doesn't stop going up. It keeps it increasing, right, until we get here to 0. So our interval of increase would be from -4 all the way to 0. And again, parentheses, because the point of inflection or change in direction is going there. And then a constant interval happens next, starting where? 0 all the way to 3. And then what happens? Got another decreasing interval from 3 to 6. And then our domain stops. And I unplugged the There we go. Sorry. So we have 2 decreasing intervals, 1 increasing interval, and 1 constant interval. There's no rule that says you have to have some of all of those. Some of the graphs you're going to have some decreasing, some increasing, some that are just constant. It's just finding those things. All right. Now, let's see here. Local maxes and local mins, and absolute maxes and absolute mins. Okay, we're going to talk about those in theory here, and then do something with the calculator to help us find that. So local max. Local maximums and technically local minimums occur within a certain interval. So you would have, if I ask you for a local max or a local min, I would need to know, like, locally where it's at, between what interval. So if I said, okay, between -5 and +3, what's the local max or local min? If I said local max, you're looking for the highest point in between those two x values. If I ask for local min or local minimum, I'm looking for the lowest point in between those two values. Local maxes and local mins happen within a certain interval, and they're going to have to tell you what interval that's in. Okay? Absolute maxes and mins. Hello? Can I help you? 202 for 140? Math 1? 100 is scheduled for 202, but I was assuming that was a mistake. And we don't meet until 5:40.
Okay.
5:45 is what time we meet.
Thank you.
Yeah.
It is 202.
That's what's on my schedule. I hope it's in here, actually. I'd rather move in here if there's not a class in here. Okay. Yes, ma'am. Yes, ma'am. Thank you, Miss Catherine. Okay, so absolute maxes or maximums or minimums. If something is absolute, it's not restricted, right? It's over the entire domain. Okay, so an absolute is the absolute maximum would be the highest point for the entire domain. A absolute minimum would be the lowest point for the entire domain. Absolute maxes and absolute mins don't always exist. Okay, if you had a graph that was drawn and you had something like this, does that have an absolute maximum? No, it keeps going forever up, right? But it does have an absolute minimum, right? It's got a lowest point. It's that, that's a parabola, it's the vertex. It's that point right there. That would be your absolute minimum. If you ask for a local maximum or minimum, then and you put a window on it and say it's only in between these 2 points, then you can always have that. But absolute maxes and mins don't always exist. Okay, so there may not be an absolute max or an absolute min, depending on the problem that you're given. Okay, all right. So let's look at a problem or an equation and use our graphic calculator to help us kind of figure out some of this stuff. So, what letter we're on here? H. So let's say we had f of x is equal to 3x cubed minus 7x plus 1. Okay? 3x cubed minus 7x plus 1. I don't know, I know what that graph looks like. You may not. I'm pretty familiar with it, but our graphic calculator really knows what it looks like. So I'm just typing that in. Minus 7x and then plus 1. All right. If I want my graphing calculator to graph that, one of the things you want to make sure as you're getting used to using the graphing calculator is that your plots are turned off. Notice how none of mine are darkened in. If you have one that's darkened in on your graphing calculator, you need to arrow up here and find the one that's darkened in and press enter. See how I've got that one darkened in now? If I go up here and I press enter and turn it off, it'll keep things from going wrong when I go to graph that. Once I've done that, I'm gonna hit graph, and I see this picture coming up. If you don't see that picture, hit zoom, then the number 6, and it'll set your window to the default window, and you should get the same picture as I've got there if you typed in the equation correctly. Now, in that picture, we see a lot of things happening. Would this particular graph have an absolute minimum? No, because what does this little leg here do? Keeps going, right? And this one, if I ask about absolute maximum, would it have one? No, this keeps going on forever across the entire domain. What's the domain of that function that we just typed in? Negative infinity to positive infinity. We didn't have any red flags, so that's what the domain is, all real numbers for that. Now, if I said, okay, between the interval of -3 to +3, find a local maximum, what would be where would the local maximum be? From -3 to +3. Be that spot right there, wouldn't it? Yeah. That would be a local maximum. Because we see there's an interval of increase here, and then an interval of decrease. That's where local maximums happen. Is the point of inflection of a interval of increase and interval of decrease. It's where they change directions. So there's a local max right there. How do we get that ordered pair? So the ordered pairs is, you can do a couple of different things. One thing would be hit the trace button and then kind of scoot around here till you got close to it. And, we're guessing it's like -1, +5. That's close. But we could get a better answer with that. With the graphing calculator, it can do some neat things. And one of those things it can do is it can calculate a local max for you. So if I hit second and then trace and calculate, look at options 3 and 4, maximum and minimum. But it can calculate those for you. So I'm going to get a maximum out of that. And it's going to ask for a left bound and a right bound. If it's asking for a left bound, that's to the left of that. So I just need to be to the left of that. So I'm going to move my little cursor until I know I'm to the left of where a local maximum would be. And I'm hitting enter. And then it asks for a right bound. So I'm going to move to the right of where that is. I'm just going to make sure I'm to the right of it. And then hit enter. And then it says guess. Well, you probably want to get close to that so it doesn't confuse itself. So I'm just going to get close. That's where we thought it was a while ago. And then I'm going to hit enter. We were really, really close. -0.88 and +5.12 is the local maximum there. We can use the graphing calculator to help us find that if we've got the equation. If they draw you a graph on the quiz, use that graph that's drawn. You should be able to find it that way. But if you've got an equation, you can use your graphing calculator to help you find those things. And they would tell you the interval. So local max at negative 0.88 and 5.12. Let's find that local min. So I'm going to go over here. I'm going to hit second calc or second trace to get to calculate on a minimum, and I need a left bound. So I know the local minimum's over here in this little trough area. So I'm just going to get, left bound of that, right bound, just get past it. We're over there. That's a good spot. Guess I'm just going to go down there and get close. That's pretty close. Hit enter, and it finds it positive 0.88, negative 3.12. Negative 3.12 has the local minimum there. So local maxes and local mins, find an in between an interval, and they would tell you. So over the interval, from -3 to +3. Local max and min. That's what we were doing there. Okay, so they'll tell you an interval, say find local maxes and min over that interval out of that. Okay, so within this kind of thing we've got going on, we're looking at pieces of graph. Sometimes in a graph, we want to look at the average rate of change. Average rate of change in a math class, a rate of change can also be called a what? Anybody remember? Starts with an S, ends with a slope. The average rate of change is slope. It's change in Y over change in X. The formula in a college algebra book looks like this. In Algebra 1 or 7th grade math, now it looks like this. M equals Y2 minus Y1 over X2 minus X1. Slope. It's the slope formula. So this is the college algebra notation over on the left. This is the makes better sense notation over here on the right, because that's the way you've seen it your entire life. Okay, so change in Y over change in X. That's all it is. So if we're going to find the average rate of change, we need two ordered pairs to do that with. Okay, so if we had a function and we want to find the average rate of change for f of x over 1, 3. We're on example I. And here's our function, 2x squared minus 5x. It's important to keep in mind that that is not an ordered pair. It says over 1, 3. That is an interval. So that means both of those 1s and 3s are what kind of values? They're x values, okay? So these are your x1 and x2s for the slope formula, x1, x2, all right? So what we need to find is what's going on at f of 1 and what's going on at f of 3, so that we can get a y value that goes with that. Once we get two ordered pairs, slope formula is easy, right? But you got to have two ordered pairs to do it. So we plug these in to x in that function. 2 times 1 squared minus 5 times 1. Ever how you do that problem, I don't care if you use a calculator, that's fine. Paid $100 for it, might as well use the thing. So 2 minus 5, negative 3. And 18 minus 15, 3, positive 3. So we have two ordered pairs. we have the ordered pairs 1, -3, and 3, 3. Use those in the slope formula. 3 minus -3, 3 minus 1. 6 over 2, 3. 3 is your average rate of change. You're the best. Thank you. All right. Average rate of change. Slope. Nothing more than that. Okay? Now, that seems too easy. So let's add something to it. Said every math teacher ever. Let's put the alphabet in here. And let's find a secant line. Does anybody remember what a secant line is from geometry in high school? It has to do with a circle. It's a line that intersects a circle how many times? Twice. Okay? A secant line can also exist for functions. I'm impressed. That's good. Nobody ever remembers anything from geometry. You only take it one class out of 4. I hadn't taught geometry in a while, but I miss it. So a secant line is a line y equals mx plus b. Equation of a line, right? Slope intercept form of a line. That's what we've done for a long time over a given interval. All right. So if we want to find the equation of a secant line, we got to have two things. We got to have the slope, and then we got to have what? The y-intercept. Okay? We got to find those two things over an interval. So we're going to get an interval for this. They're going to say find the secant line over this interval. So if we take a little bit of the work we've done here with example I, and we say f of x is equal to 2x squared minus 5x. That's the same equation from example I over the interval 1 to 3. That's the same one we just did. And we want to find the secant line, the equation of the secant line. We're going to do the exact same things that we did to find the average rate of change. We find f of 1 and get -3. We find f of 3 and get +3. So we got those two ordered pairs. We did the work just a minute ago where we said 3 minus -3 over 3 minus 1 and got 6 over 2, which is 3. That's our slope. How do we find the y-intercept? This is the part everybody falls apart on. But I think I'm going to be impressed because somebody's going to know how to do it. If I got an equation, y equals mx plus b, and I know m, what else do I know that's up here on the screen that I could use to find b? I know. Go ahead. Both of you together. You got a y, and I got 2 points on the graph. Those points have y values, but they also have x values. We got a y and an x. We need to pick one of those ordered pairs. It doesn't matter which one. Pick the one you think's the easiest. I personally think 3, 3 is easier than 1, -3 because I don't have to worry about a negative sign, and I can't screw up which way I put them in. Right? So no matter which way I put it in, I've got 3 in for y and 3 in for x, and I can find out what b is. 3 equals 9 plus b. Subtract 9. B is equal to -6. So my equation of the secant line, that's my next thing. That's the big thing. Y equals 3x minus 6. equation of the secant line. That's what that is. The secant line. Fun times. Okay. All right. Let's do one more and we're done for the evening. Okay. Okay. Last example of the day, f of x, 3x squared minus 2x plus 3 over the interval from -2 to +1. Find the secant line. Okay, so if we're going to find the secant line, what's the first thing we need to find? The slope. To find the slope, what do we need to find? What do you got to have to find slope? Ordered pairs. Where are we getting those? The interval. So f of -2 and f of 1. So if I plug in -2, that'd be 4 times 3 is 12 minus -4. So it'll be 16 plus 3 is 19. Is that right? Plug in 1. 3 minus 2 is 1 plus 3 is 4. So I get ordered pairs, -2, 19, and 1, 4. Let's find the slope. 19 minus 4 over -2 minus 1. Be 15 over -3. Ooh, that works out great. It's like he planned it that way. It's -5. Slope. And then, what do we do from there? Plug it back into the y equals mx plus b, -5x plus b, and then what do we do? Got to find b, so we use what? One of the ordered pairs. Does it matter which one? Pick the easiest one you think is there. I'm going with 1, 4, because I'm pretty sure I can multiply by 1. So y is 4, x is 1, I'm finding b. It's -5 plus b is equal to 4. I would add 5 to both sides. 9 is equal to b. So my secant line is y equals -5x plus 9. If I were to graph that original equation and then this secant line, I would see it intersecting that graph of the f of x at those ordered pairs, -2, 19, and 1, 4. They would cross those, okay? So that's secant lines. Getting the equation of the secant lines. Got to find slope. That's the average rate of change. Remember, those are the same things. Slope and average rate of change. Tie those together. You're probably not going to see the word slope on a Canvas quiz or on a real test on the exam in here. You're going to see average rate of change because that's the college word, okay? You're not going to get the formula. Better know them, okay? Know your formulas. All right. Problems for this section would be 237, 1 through 79, any of those. I don't really suggest doing all of any of these that I've suggested. I'd say do a few from each. They're like subsets. Do a few from each one, maybe one at the beginning, the middle, and the end of each one. And if you have trouble with a section, you check it in the back of your textbook and you have trouble, then go back and do some more of those and try to practice some more on those. Definitely email me questions if you have them for this particular